Alright, good morning. So this is the second lesson on magnetism. Our first one was kind of just the basics, and now we're going into fields of magnets. So last lesson we learned that there's permanent magnets that have a north and a south side, and you can have field lines that go from the north generally to the south. They go outward from the north, and they usually get attracted to the south. So it's kind of like or electrostatics, where you have a positive test charge and it goes away from the positive to the negative, but this time it's a north test charge that goes from the north to the south side. Alright, so that's what we learned last time. Another thing that we kind of learned is the right hand rule. So if you have some sort of wire, and say you have a current going, let's say, positive to negative over here. Okay, so you're going from the positive to the negative in that direction. So you use your right hand, your thumb points in the direction of the current, and your fingers curl around what way the magnetic field goes. So it goes in circles around this wire in this way, like that. Okay, and it goes around like this, around the whole wire. So every wire that has a current through it makes a magnetic field. That's what we learned last day. Another thing that we learned was, this is a really bad example of a solenoid. If you kind of curl it around in a spiral shape like this, you make something that's called a solenoid. And if you have a current going through there, again, every wire that has a current makes a small magnetic field. So that means all this wire is making a magnetic field. Well, when you add it all up in kind of the way that it makes a magnet just like this, the north and the south side. Okay, but generally, you curl your fingers in the direction the current's going. Again, this is kind of a different form of the right hand rule. Your curled fingers go in the direction of the current this time, and this time the current's kind of going that way. So my thumb would point in the north direction. Okay, my thumb would point in the north direction. Just making sure I have it right. Yeah. So those are the two different right-hand rules that we saw from last day, and it doesn't have anything to do with the right-hand motor rule, which was at the end of the day, which was a bit misleading, but we'll go through that today. Last day we saw that magnets, I think that was most of the stuff that we did the first day. Okay, anyways, we'll start going through the actual lesson this time. Oh, one thing, this is what I wanted to add. Last day, if you put an iron core inside the solenoid, it turns this magnet stronger, okay, much stronger. So that's called an electromagnet. All right. So that is that. Now let's go into fields. So here we have something called magnetic field strength. So you can guess that since there's arrow and field lines that you have some sort of magnetic field strength, right? Where you have more arrows, it might be a stronger field strength here than it would be out here. Okay, so there certain spots in an area will have certain values given to it to create a field strength. Okay, so let's just recall what electric field strength was. We know gravity field strength is acceleration. But electric fields we knew was the force per charge of the test charge. Okay, so that's what it was, electric fields, and we made it E to be the variable. Okay, and it was units newtons per coulomb of charge. Okay, so now if we want to look at magnetic fields, we're going to use the variable B instead of E. It's still going to be a force at a particular spot, but it's per charge as well. So it's per charge of the test charge, the very small test charge, but also per speed of the test charge. So the thing that makes magnetism different than electrostatics is that it depends on the speed of the particle. Okay, so if the particle is not moving, it's really divided by 0, so that doesn't make any sense. But if it's a very small speed, it's essentially going to be not really affected. Alright, so that's the field strength there. Okay, and if we rearrange it, we can solve it for F, and then our force would be our field strength value B times our test charge value times our speed of our test charge. Okay, so the interesting thing about magnets is the speed of something moving through them makes them more relevant. So here our force on this particle is going to be based off whatever the magnetic field value is at that spot times the charge of the particle times how fast it's going. Okay, what unit does B use in? So if we look at E, that was newtons per coulomb. This is Newton per coulomb per meter per second, or also known as a Tesla, which uses the unit T. Okay, if you want to look more at the units, it's newtons per coulomb meter per second. Okay, another way to think of it is coulomb divided by second is called an amp, so it's a newton per amp meter. That's another way, but besides the fact, you just have to know that B uses the units Tesla. Okay. All right. So if we look at this example, we have these, say, these straight lines, which is a magnetic field of B. Okay, and this charge is traveling straight perpendicular through these field lines. So generally, there's going to be a force applied because it's a charge and it's going at a certain speed through a magnetic field. So what is this force? It's just going to be the magnetic field times the charge times the speed it's going. But what's the direction of the force? That's a very unique thing. Is the direction of the force, you actually have to use the right hand motor rule, which I have it listed at the end of this lesson. But what you do is you take your right hand again, you open it up, you put your four fingers facing the direction of the field. Okay, so going that way. And then your thumb must point in the direction of the charge. Okay, so I'm right now. And then your open palm, which is this side of my hand, is going to face the direction that the force applies on the charge. Okay, so it's going into the desk, my palm is. So that means the force applied to this charge is going to be downward or into the page. Okay, picture a 3D model, it's going to be going pushing down. So the interesting thing is these B arrows don't actually tell you the direction of the force. It's not actually going that way, it's actually going into the page. Okay, that's why the right hand motor rule exists and why it's important. Alright, so now it says, but this only applies if the velocity of a particle is directly perpendicular to the B field direction, just like in this picture. But what if it's going at an angle like that? Then what would it be? Okay, so it ends up saying that it would just be the component that is perpendicular, which is V sine theta. Okay, so it's the component that is perpendicular they kind of pay attention to, where theta is the angle in respect to the direction. So overall, the formula is not really this. This is only for perpendicular motion. It's really this, BQv sine theta. Okay, because sine theta is always less than 1, so the most you could have is when it's perpendicular. Okay, let's look at two sample questions after learning what we just learned. So say an electron is traveling the speed of 2 million, I think, meters per second, moves in a direction perpendicular to a magnetic field strength 0.025 teslas. Okay, what is the force acting on the electron? It's going to be F equals BQv. It's really V sine theta, but here they're saying perpendicular, so sine theta would be 1. So what's our force that's being applied? Well, our B value is 0.025 teslas. Our charge is going to be, well, since it's an electron, we have to look at our formula sheet and see what charge an electron has, and it's 1.602 times 10 to the negative 19 coulombs. It's a very small charge. And then what's our speed? 2 million meters per second. So overall our force, if I calculate this in my calculator, is 8.01 times 10 to the negative 15 newtons. So this electron is going to feel that tiny force on it. when it's in a magnetic field. What is the magnitude and direction of the acceleration? Okay, so in this question, the magnitude of the acceleration, we know the force is 8.01 times 10 to the negative 15 newtons. And then overall, it's mass times acceleration, which gives you acceleration, or it gives you force. So we have to divide by m, and we get an acceleration of 8.01 times 10 to the negative 15 divided by the mass of the electron. Okay, so overall the mass of the electron, I don't have in front of me, but I know it's a very, very small number. Let's see if it's in this book. Yeah, I don't have it on me at the moment, but you divide by the mass of the electron and you'd end up getting its acceleration. But what's the direction of the acceleration? Well, you have to know what direction the force is. So right-hand motor rule, you would put your fingers towards the field direction, your thumb towards the electron's speed direction, and then the force would be directly perpendicular to both of those, which would be straight down into the page in my example. So, so you'd have to use right-hand motor rule. Thumb in movement direction, and fingers in field direction. And then that means your palm is in the force direction. Alright, so let's move on to the next page. We have something next to do with the solenoid, which we already know what that is. It's a current going through just a coiled wire, which makes a magnet. And if you put your fingers, your right hand, in the direction of the current, and then your thumb would point in the north direction of the magnet. And as we can see, it's north there, south there. And it mimics a magnet here. Okay, so this person named Ampere derived many experiments that deduce magnetic field is uniform or the same everywhere on the inside of this solenoid. You can see all the lines kind of are like the same direction and the same magnitude. So he found out that it is uniform everywhere inside that solenoid. And the one thing to note is if you look at the directions of the arrows, they go from south to north on the inside, but on the outside they go from north to south. So oppositely goes in the wrong direction, right? Because normally field lines go from north to south, but on the inside of a solenoid, they go from south to north. Okay, it's kind of like a black hole. All right, so when we're looking at electricity, we could find the force on a particle by using this here, kind of like Newton's universal law of gravitation, but Coulomb's law. We could use that to find the force of a particle. This leads us to saying that the field value at a particular spot is the constant times the source charge divided by the distance from the source charge squared. But for magnetism, we don't have this equation. So how do we calculate field strength? We haven't talked about how to find the B value, the Tesla value of a magnet. How do you find that? So it turns out, when you're dealing with a solenoid at least, the number of turns of wire per unit length, or the number of turns per meter, and the current going through the wire tells you what your B value is going to be. Okay, but this is the B value that you'll get on the inside of the solenoid only. Okay, so it's talking about the inside of the solenoid. Outside, they still don't know what the magnetic field will be, but here, if you know the number of turns and then current going through your solenoid, you'll know the B value everywhere inside that solenoid. Okay, and it turns out that it's mu naught times number of turns times current divided by the length of the solenoid will give you your B value. And another way to write it is your N is the same as N divided by L. Okay, the small n there. Let's see, mu naught is 4 pi times 10 to the negative 7 Tesla meters per amps. It's just a constant. It's like the K value. And it's called permeability of free space. And then we go to N, which is giant N divided by giant L, which is the number of turns per meter of solenoid. Okay, that's what N means. You could also calculate it just by counting the number of turns in your solenoid divided by the length of the solenoid. And then we have current. I is the current going through the wire in amps. And if we remember what amps are, it's units coulombs per second. It's the number of coulombs of charge that travel through per second. Alright, so that's our field value we can calculate for solenoids. That's why solenoids are so nice, because you can find a uniform magnetic field by using this equation. Alright, let's look at this question. So here's a picture of kind of a 3D solenoid, and you can kind of see the magnetic field lines all going into it. Alright, so a solenoid is 15 centimeters long, has 250 turns. What is the magnetic field strength inside the solenoid if the current in the coils is 3.8 amps? So we can have B is mu naught number of turns times the current divided by how long the solenoid is will give us our B value. Okay. And overall it's going to be going from south to north direction, but let's find out what our magnetic field strength is in Newton per coulomb per meter per second, or in Teslas. So our mu naught is 4 pi times 10 to the negative 7, just a constant. Our number of turns, they say, is 250. Our current, they say, is 3.8 amps. And then our length of our solenoid is 15 centimeters, but we always have to do it in meters, so it's 0.15 meters. And that makes our B value equal to 0.00796. What unit do I put? It's magnetic field strength, so Teslas. So strong this solenoid is. So if you have 250 current turns and 3.8 amps going through that solenoid, you'll have that much Tesla. Okay. What is the force of a particle in a solenoid in respect to its turn number and current? Okay. So this is a tough question, but I made it on purpose just to see if we can combine two equations. So if we look at our first page, we have this equation, F equals BQv sine theta, which would give us our force of a particle. Okay, so if we start out with that, we can have F equals BQv sine theta of a particle. Okay, but we now know what the B value of a solenoid is. So since it's a solenoid, we can plug this now into this equation. So let's find out what the force would be. Our B would be mu naught N times L, I over L, and then we can write the rest, Q V sine theta. And there we have it. So our force would be mu naught number of turns times the current of the solenoid times the charge of the test charge times V times the sine theta divided by how long the solenoid is. Okay? Not that we have to remember this, but that would be one way to get a force if you had different values to work with. Alright, so now we go on to the last page. It's really just kind of information, but it's interesting. Another version of the force equation here. So they say another version. What's our first version? Well, if we go back to our original page, our original version. Force is magnetic field times charge of the test charge times the velocity of the test charge. Well, there's another way. So here, from the first page, we see that it's this. Suppose you have a current going through a single wire in the middle of a magnet. Okay? So just like this. We have a magnet north-south direction. We have your field lines, which go from north to south, and then you have your wire straight perpendicular right in the middle of those two. Okay, so here your speed of, say, a particle in that wire goes from here to here in a certain time, or your length divided by time. So velocity can really just be length divided by time of the wire. Okay, so where length is, L is the length of the current, and T is the amount of time it takes to travel that distance. So this leads us to, now instead of BQV, we have BQ L over T. And since our current over time, or no, charge over time is equal to current, because current amps are coulombs per second, we can rewrite this as B. Instead of the Q over T, we're going to write an I, and then the L is by itself there. Okay, so that T we just shifted over to be underneath the Q. So now we can also notice that F is equal to your magnetic field strength times your current going through this wire times the length of the wire. And you're also going to get the force that applies. You can see there's an arrow aiming down on this. So if we use our right hand rule, we can see what direction these field lines or the force on this wire is going to be. So you put your fingers in the direction of the field strength, you put your thumb in the direction of the current. In this case, the current is going that way. They don't tell you, but if the force was down like it is, then it would have to be going that way. And then your palm points in the direction that the force is being applied on this wire. So it's going to be forced down by being in that magnetic field. So force is magnetic strength multiplied by current of wire multiplied by length of the wire through the field. Alright, so that's pretty interesting. Okay. Alright, and one thing to note is you can also formulate it for a solenoid. So we know force is B times I times L, and we know our B value for a solenoid is mu naught times N times the current of the solenoid divided by the length of the solenoid. And then we have I, which is the current of the wire, times your L. Okay? But your L in this case is going to be the same as your solenoid. Okay? So it's going to be big L. And then we notice that those are going to cancel off. So overall we can go force is mu naught N current of the solenoid times current of the wire, and that'll give you the force on the wire. Okay, so for a solenoid. So that's just if you were interested. I wouldn't worry too much about this. This is the equation you want to use. Alright, so right hand motor rule. In the case of a current in a magnetic field, this is just telling you what the true right hand rule is. Your thumb points in the direction of the current from positive to negative. Your fingers point in the direction of the electric field strength, which is north to south. And then your palm tells you the direction of the force. Alright. So that's the right hand motor rule. Last of all is just a little blurb in case you're interested about electric motors. So this is what an electric motor is. It's really just magnets. So we know that there's a current in a magnetic field, and the magnetic field applies a force on the currented wire. Okay, we just saw that from up there. But what if you place a loop in this magnetic field? Well, if the current is going, say, around there like that, and then back up this side, well, right hand rule tells us that the force here would be down here, but this one, the force comes back the other way. And when it comes back the other way, it actually has a force the opposite way because of directions. And I would test the right-hand motor rule yourself to assure yourself that that would be the case. That would cause this wire to twist like that, okay? And then it would stop right there. So that would be the right-hand motor rule. This wire here is called an armature, okay? And then they have this kind of circle thing here, which we call a split ring commutator, which, because it's split there, when it turns, it essentially switches the direction of the current. So every time it does a half turn, it switches the current to the other direction. So it went down and up, and then when you get to that certain spot, it switches current direction, and then this one would then feel a force downward, and this one would feel a force upward. So essentially what's going to happen is this thing is going to turn indefinitely. It's going to keep turning around because of this split, this current which changes the current direction, and because of this armature which has a loop. Okay, so this is called an electric motor. You apply a current inside a magnet. Okay, a current inside a magnet, and it produces movement. Okay, so that's what a motor is. So it's just a current in a magnet. If it's from direct current, then you need this split ring commutator to change the direction of the current so that it keeps spinning. But if it's alternating current, like a household outlet, it doesn't need to because it's already alternating the direction really quickly. Okay, but that's what an electric motor is, just kind of aside. All right, thank you.